So third session of geometrical optics, let me start with a quick recap of the important aspect that we learned last time, which was, towards the end of last time what we learned, which was about refraction at a plane surface. So we saw for refraction at the plane surface. Now let me invert the diagram compared to what we done last time. So suppose we have this as the plane boundary, and this side has refractive index mu2, whereas this side has refractive index mu1. So for any object, point object kept over here, being viewed normally from this side. So the observer is viewing this object with a normal kind of vision. Then the position of the object seen becomes, let's say, like this, where if this distance is d, that is the real depth, this distance becomes d prime, the apparent depth. And we have the formula, the apparent depth is the real depth upon refractive index of medium 2 with respect to 1. Where, remember, the convention is that the rays are refracting from medium 2 to medium 1. Okay, so that's how you remember this. Okay. So as you can see, d prime is less than d if mu2 is greater than mu1. That is from denser to rarer. Whereas d prime can also become greater than d if mu2 is less than mu1, from rarer to denser. So let us look at some application questions of this kind of situation. And of course, with this we have the spherical mirrors, which we have done a very detailed analysis of by now, including the analysis of what we call virtual objects and things like that. So extremely important, those things are. So let's look at simple example like this. Now these examples that I'm doing, they will cover partly the doubts that you have in homework also. So very similar type of questions. Okay. But yeah, we will discuss some of those specific questions from your homework also. So this is a glass slab, and it has refractive index 1.5 or 3/2. This is air on this side. Okay. Now what we've done is we've silvered one side of the glass slab. We've silvered this, but it's a thick glass slab. So it's not like a thin plane mirror. Okay, so this is a mirror on this side. Now this thickness of the glass slab is, let us say, 24 centimeters. And in front of this we have an object which is at a distance of, say, 18 centimeters, and we have an observer somewhere right behind over here. So we have to find the position of the object O's image seen in the mirror with respect to O as seen by the observer. Okay, so just start working on this, we will discuss. So the first thing I advise you to do in a question like this is try and first understand the ray diagram. Formula and all is fine, what all will apply, we'll discuss very soon. But what is happening in the ray diagram? So from that you will understand how many events are happening. And as you understand how many events are happening in series, one after the other, you will be able to identify how to apply the required formula. So the only formula we require in this is the real depth apparent depth formula, which I have written above, and the plane mirror formula, which you obviously know. So just visualize the ray diagram and try to understand how to get this. Okay. So the observer will be able to see the object directly, and somewhere behind he will be able to see the image of the object. So you have to find with respect to the object, that is from the object, at how much distance behind he sees the image. Not getting correct answers so far. Okay, so let me start by explaining to you in the ray diagram what all is happening. Then you can try and do the calculation part yourself. Uh, Still not correct. Okay, now let's consider some rays. So the normal one just retraces its path. But let us consider what is happening to any paraxial ray, because images will be formed by paraxial rays. So this ray will tend to bend towards the normal. Okay. So that's your first event. So when we produce this refracted ray back, it appear to be coming from somewhere here. All the answers you people are giving me are missing at least one event out of the events which are happening. Okay, so I'm just explaining that's why in detail to you what's happening over here. So this is my I1. Okay. Now these rays which are incident on the mirror, they will reflect. That is the next thing. Okay. So kind of run out of real estate here, but they will appear to be coming from some point behind. So somewhere behind, I would have my second image. Somewhere behind. And then this ray here would again be refracting, and this time when it refracts, it will bend away from the normal. So it will go like this. It appears to be coming from some point over here. This point here becomes my third and final image. Okay. Yeah, I've got one correct answer now. So far. Okay, so these are all the events that are happening. Okay. So now we have to start using the various formulae. So first event is refraction from air to glass. So for that the object is O and the image is I1. From inside the glass, this refracted ray, it appears to be coming from I1. So if I just name this point P over here, and also I name this point Q over here, the real depth, so called, is PO, and the apparent depth, so called, is PI1. So I have PI1 is equal to real depth PO divided by refractive index of air with respect to glass, because the refraction is happening from air to glass. So that means PI1 is equal to refractive index of glass with respect to air multiplied by PO. So it is 3 by 2 times, I think we are taking this as 18 centimeters. So 27 centimeters. That is the distance PI1. Okay. So that's the first event. Now the second event that's reflection at a plane mirror. Okay. So the object for that one is now I1 and the image is I2. So object distance should be equal to image distance. So QI1 or rather QI2 image distance should be equal to QI1. So that should be equal to the thickness plus this. So the thickness was 24 centimeters and this was 27 centimeters, so that is 51 centimeters. So the mirror forms an image 51 centimeters behind itself. That is where your I2 will be somewhere behind. You know, when you continue this line, I2 is somewhere behind like that. Now again, that is not the image seen by the observer here, because the rays which are coming by reflection, that is these rays, they are again suffering another refraction over here. So for this interface, glass to air, that I2 becomes the object. I2 becomes the object and I3 becomes the final image. Okay, so the third and final event is refraction from glass to air. So here for this one the object is I2. So the object distance, the real depth, will be PI2, which will be the thickness of the glass plus the distance behind. So that is 75 centimeters. And the image will be I3. So we'll take the apparent depth as PI3, which we want to find out. So the apparent depth will be the real depth divided by refractive index of glass with respect to air, because it's going from glass to air. So this will become 75 divided by 3 by 2. So it becomes 50 centimeters. Okay. So from this point to where this final image is, that is so much. So with respect to the object, it's another 18 centimeters. Therefore, OI3, that is position of image with respect to the object as seen normally from behind. That is going to be 50 plus 24. Sorry, 50 plus 18 minus 68 centimeters. Okay, so this is my final answer. This one. Okay, so I'll just minimize a little for you to catch each of the events. Okay, people. So hope this method is fully clear. Okay, now, very interesting, we can cross-verify this with another method, which will also be shorter to work out, but which will be using a bit of a trick. Okay. And that trick is like this, that for a bit, just forget about the object and all that, and let's just concentrate on the arrangement which we have, which is a slab of glass like this. Now imagine if somebody was viewing this from here, and you have, like, a speck of dust or something over here. So where would that speck of dust appear to be? It would appear to be somewhere over here, because it's inside glass. So this real depth of the glass was, I think, 24 centimeters the thickness, and this apparent depth, suppose it is x. This one. So this x would be equal to 24 divided by refractive index of glass with respect to air, because the refraction is happening from glass to air. So anyway, so this would appear to be 16 centimeters. So now that basically means that this mirror, which is at a depth of 24 centimeters from this point, but it's at a depth of 24 inside glass. So this is equivalent to just a plane mirror, but that plane mirror is closer. That plane mirror should be here. Okay, such that this is now 16. Okay. So now if I placed an object, let's say A over here, it was in front by whatever 18 centimeters, and my equivalent diagram, that object is over here, where this distance is 18 centimeters. So its image as seen by this guy should be behind over here at a distance of, let's say, y, and y should be equal to the object distance, so that is 16 plus 18. So that is how much? 34 centimeters. So now you can see that E prime is 16 centimeters. So this is like reducing the system to an equivalent mirror which is closer, because there is a glass slab in front of it. This is this kind of method. So this is an alternate way of understanding the question. So I hope this will be clear, people. So yeah, geometrical optics does have situations where there's a bit of tricks and all involved, which can help you save time in how you solve problems and save the number of calculations and all. But at the same time, in the beginning, it is always useful, even if you're trying to solve by the shortcut method. It's always useful if you first, in your mind at least, you understand the ray diagram. So you understand what all events are happening. That makes it clear to understand, what direct concept you can apply. So it is only the ray diagram which actually tells you how many times light is refracting, reflecting, and what all kind of phenomena are happening. So this is one typical type of question. Okay. Now another very typical type of question which you would have seen quite a few of is combination of refraction and reflection. So let's pick up a typical question like this. So these questions that I am discussing, they will mostly cover all your homework question types also. Okay, so now in the next example, we have something like this. We have, let's say, convex mirror with a radius of curvature, sorry, concave mirror. The radius of curvature of 60 centimeters, and this point is its pole. Now what we have also done is we put you've seen plenty of questions like this. You put layer of water over here, such that the height of the water layer at coinciding with the principal axis, that height water has refractive index 4 by 3. Now that height is something. Let us say it is whatever, 2 centimeters or something. Now we want to keep a point object, like maybe an LED bulb or something like that, as a source of light or something, at some position over here, such that we get the image of that at the object itself. Okay, so a point source O is placed on the principal axis such that its image due to reflection by the system coincides or overlaps with itself. So find the distance of the object from the pole at which we should place it so that this happens. This is air, of course. So this is another application of that real depth apparent depth formula. And of course, along with that, the plane mirror, the spherical mirror formula. So as I was discussing in a couple of previous questions earlier, whenever your final object coincides with your original, your final image coincides with your original object, it is always a situation where there is retracing of rays. So there is retracing of rays. That means the reflection will be happening with normal incidence, so that the reflected rays just reverse the path of the incident rays. In the case of spherical mirror, that only happens when the rays are coming from its center of curvature. Okay, so that is the concept that you apply over here. Just apply this concept over here, and you get the answer. Yeah, Ganesh, it appears to be correct. Soumyadip, check your solution again. Okay, so once again, let us first think in terms of ray diagram. What we want should be the occurrence over here. Now, for the point object that we placed here, let's say, now let's say this height is x from the water level, and then further from the pole, this h. Now the situation that we're looking for is actually this. Rays incident here, they will tend to bend towards the normal. And then they are incident on this. Okay, so this is the first event. Now we want that they should retrace their path. They should go back here, and this is what should happen. So that means when I produce this refracted ray back, like this, let's say, it should be appearing to come from here, which is the first image because of refraction from air to glass, air to water. And that should be basically what? That should be the center of curvature. You're understanding the point over here. Okay, so the first event, it is air to water at a plane surface. So the object is O and the image is I1, and let us write this image's position as x prime with respect to the water surface. So real depth is x, apparent depth is x prime. So x prime should be equal to x upon refractive index of air with respect to water, because the refraction is happening from air to water. So that means it should be equal to 4 by 3x. Okay, so that's the first thing. Now the second event that we want, that is reflection. Okay, we will just have to hang on a minute here. My system has lost connectivity. So in the meantime, while I'm just rebooting that, I will just tell you what to do in this question. You can try it out yourself. Now, as you can see in the ray diagram very clearly. Alright, so I will just take you through the whole thing again once while you are writing this down. So as we saw, the first event resulted in refraction from air to water, and that's why from underwater, if you are seeing that object O, it appears to be at a distance of 4 by 3 times x, not at a distance of x, okay? Because you are seeing it from a denser medium. Now those rays which are in water, they are incident on the mirror. So that's where our second event comes in, that the rays which are incident on the mirror, they should be retracing their path. Only then the further the rays that go back in air will also be retracing their path. Okay, so that concept we are using. So for retracing of the reflected rays, we want that the incidence at the mirror should be normal. That means the rays which are incident on the mirror should appear to be coming from which point? From its center of curvature. So in this case, the rays which are incident on the concave mirror below, they appear to be coming from I1. They don't appear to be coming from O, because remember the incident rays on it are the refracted rays inside water. Okay, so I1 should be the point which should be at the center of curvature. So that is the concept of this question. That is a concept we finally applied over here, that I1 is at the center of curvature. Okay, people, so hope this is clear. Okay, next, I'll refer you to one of the questions in the homework. Okay, just hang on. So let's pick up a question from H.C. Verma. Let's do question number 15, 1-5. Okay, question number 15, 1-5 from H.C. Verma. So I'll just refer you the question again. So this is a question where none of the formulae we have applied will be directly happening over here. You'll have to use basically the principle of refraction and Snell's law. So question number 15 in HCV is like this. It says that a pole of length 1 meter stands half dipped in a swimming pool of water, the level of water being 50 centimeters higher than the bed. Refractive index of water is 4/3 and sunlight is coming at an angle of 45 degrees. So we have to find the length of the shadow. Okay. So we have a pole which is vertically standing in a water bed, and the water bed, I mean, the height of the pole is 1 meter, whereas the height of water level is half of that, 0.5 meters or half a meter. And sunlight is falling on the system at 45 degrees angle to the horizontal or vertical, whichever. So to find the length of the shadow of the pole, which is cast on the bottom surface. So just try this out. Okay, people, so just referring you to the solution of that question. Right, so the situation is like this, that we have a vertical pole like this, let's say, which is 1 meter long, and we have water up to half its height. This. Now, obviously, this is the bottom surface. That's apparently the best I can do. Anyway, so we have sunlight now, which is incident like this at an angle of 45 degrees. So as you can see, this sunlight will go through, but from here the sunlight will not go through. So it casts a shadow. Now we have to see where it casts the shadow. So had this, so now you have to understand that the rays of sun over here, for example, they reach somewhere here like this. The rays of the sun they reach somewhere here like this. Okay, so this is the general path. So you can see that this one's path would have been something like this. But that is actually not there now in my system. So you can see that underwater, in the bed, this part is dark. That's the shadow. Whereas everywhere else there is sunlight which is present. So this part has sunlight coming in. This part has sunlight coming in. So now we have to just find this length. So let's go about that task now. Finding that length. So that should be pretty easy. Let's first of all work out these angles. This is I and this is R. So sine I should be equal to refractive index of water times sine R. So 1 by root 2 is equal to 4 by 3 times sine R. So no need to calculate R here. We'll just understand that sine R is 3 upon 4 root 2. Now let us see how we can make use of that to understand the position of this. Okay. and the water levels up to here. Now let's come to the ray of light, which is just about missing this point. Just think of it like that. There is a particular ray which is just about missing that point. That ray, suppose, just skimming it like this, and then followed by something like this. Okay. So this is the thing we have to concentrate on now, this diagram here. So we can see here that this distance is 0.5, this is 0.5. Okay. So this will also be 0.5 because this angle is 45. Okay. So now all we have to do is, when we drop this over here, we have to find this, how much this is, let's say, d. And then our length of the shadow will be 0.5 plus d. Got it? So वो d के लिए क्या करेंगे? We will just understand that this height is also 0.5. Okay. So this is 0.5. And this angle here is our r. This angle here is our r. So x is the unknown. Okay, so for that triangle, you can now see x upon 0.5 meters is equal to tan r. Okay. And we already know that sin r was how much? It was 3 by 4 root 2. So 4 root 2, 3. So how much is this side now? Okay. So tan r is 3 upon square root of 16 to the 32 minus 9. 32 minus 9 is how much now? 23. Okay, so you can just check my calculation, but something like this. So x, so tan r you substitute now. So you'll get the value of x, and then your length of the shadow will become 0.5 plus x. Is this clear, people? Yeah, you can use sine rule also, Ganesh. That's correct. Sine rule is in fact very favorable here because this angle is 90, this angle is r, this angle is unknown. But then in sine rule, you'll have to calculate that other angle. Achha, it will become cos r, and cos r you can easily calculate. Anyways. Alright, is this method clear? Okay, now very similar to this, there's another very interesting question in HCV, which is something like this. So I'm not going to solve that question fully. I'm just going to give you an idea of how to do it here. But it's very interesting and you should do it because it also involves quite a bit of thinking. So I have this vessel made of opaque walls. So these are opaque walls. And there's an observer somewhere over here whose line of sight is this line. This is that observer's line of sight. And if I remember correctly, this angle is exactly 45 degrees. Now, it is given to you that there is a point object somewhere over here. Okay. So obviously that the rays which are coming out from the point object, they are not reaching his eye. So he cannot see it right now. So what he does is, he makes sure that some water is poured into the system up to a certain height. so that that object becomes visible. So given that you know the object's distance from the center, or whatever, you know where the object is placed. So know this distance is d, or from the center or whatever, some distance is known. So d is known, refractive index of water is known, and obviously this side length of the tank, this is known. This is also L because this is a 45-degree angle. So L is known. So to find H so that the object O is visible. Okay, this is what we have to do. So I'll just leave you with a hint for this question. So what we have to do in this question is you have to make sure that because his line of sight is this, 45 degree. So he can either see rays which are coming from here. Okay. So this has to become the refracted ray for him. Coming from that object, this one has to become the refracted ray. So the incident ray has to be this one. It has to be coming from the object to that point. So you have to now geometrically find this condition using Snell's law. You have to make this ray the incident ray. This one has to be the incident. Just magnifying this diagram a little. This is the incident ray. You drop a perpendicular here, and this has to be your pair of I and R. Your R has to be equal to, no, the thing is we cannot apply real depth apparent depth formula here, because what is happening, it is not a normal incidence. So you cannot apply the concept of real depth and apparent depth. You are not dealing with paraxial rays. You are dealing with rays which have a high angle of incidence, because the angle of refraction only is 45 degrees. Okay. So just apply this thing now, Snell's law. So 4 by 3 sine I will be equal to sine R, and R is 45, and from that you back calculate how much this height should be. Okay. So from this point it's just trigonometry and Pythagoras theorem and combinations of these things, but these are like two exceptional questions I wanted to discuss, which are different compared to the normal application of real depth apparent depth. Question number 33, Ninad, I'll come to that. Okay, I'll come. Okay, now before I come to more doubts, there is another very useful formula that we can use, just like we use the apparent depth, real depth formula. Okay, some of you have been asking doubts on WhatsApp, so I've referred you to this formula also. And this is the formula for refraction by a refracting slab. And it need not be thin or anything. Okay. But again, the thing is that the view is normal. That kind of thing. Okay. So we have something like this. Something like a glass slab to begin with, let's say. Let's say like this. So refractive index of glass, suppose we are denoting it by mu. And the thickness of the glass slab, we're showing this thickness as P or D or whatever. Okay. Now on one side of the glass slab, we have a point object. and on the other side we have an observer who is viewing this normally. So his line of sight is normal. So there's a direct result that comes over here, that if he observes the object to be somewhere here, to him the object's image will be over here. Then there is a direct formula for this shift. This object shifts by a lateral amount of delta x. So the formula is that delta x is equal to this thickness into 1 minus 1 by mu. Okay. So what we're going to do next is we're going to prove this formula. And it's a very useful proof. And it's a very useful formula for direct application. But first let us, so how we'll prove this formula? By real depth apparent depth. Okay. So very interestingly, this amount by which it shifts is independent of the object distance. It only depends on the thickness and the refractive index of the slab. So if this object distance is x from this, okay, then it is independent of x. Okay. So let us look at the proof of this. Try this out. Okay. For the proof of this, you have to go with two refractions. But to understand in the ray diagram over here, that the rays from the object suffer two refractions before they come to this side. So one is refraction from air to glass, which will result in the rays going towards the normal. So from inside glass, this would have appeared to be further behind. But then there's refraction from glass to air, which again bends away from the normal. So it again comes in front. And apparently it comes so much in front that the final image is in front of the original object. So we can actually prove this by taking some arbitrary value of x and showing that the distance between O and I comes out to be independent of that x, and only it depends on these two things: the thickness of the slab t and the refractive index mu. So this in itself is like an exercise, it's like a problem, but we will also see how to use this very effectively directly in questions. Okay, people. So a very similar type of derivation here. Now, very good. So our point object here. Let's say a normal line. Now let's consider the first event. So refraction from air to glass will result in bending towards the normal. Like now, if you produce this back, it appears to be coming from somewhere. Here, this is the incident ray, this is the refracted ray, and this is just producing the refracted ray back. For the second incidence, which is from glass to air, the object actually becomes this one. Let me say I take this distance as x1. Already I've taken this distance as x. So the first one is from air to glass. So the apparent depth will become the real depth divided by refractive index of air with respect to glass. That will be mu x. And that is why it's greater, you can see, because mu is obviously greater than 1. So this becomes my first. Now let us consider the second event, which is refraction here from glass to air. So these incident rays will now bend away from the normal. And incidentally, these rays that come out, they will actually be parallel to this one because it's same set of angles. So when you produce them back, you see that is why they will have to meet somewhere. That is my second event. So this is the final refracted rays. And actually, this is very close to the principal axis. So in real life, imagine the rays I'm talking about are paraxial. So they're very, very close to the principal axis. They are rays which are like this. Anyway. So these rays, wherever they are intersecting, this is my final image. I2 is the final image. So now let us consider some distances. Like this one. Let's consider this distance as d prime and this whole distance as d. So for the second refraction, which is glass to air, the apparent depth d prime will be the real depth d divided by refractive index of glass with respect to air. That tells me that d prime will be equal to d, which is, by the way, how much? It is x1 plus the thickness divided by mu. So this becomes my second. Now you solve equation 1 and 2. x1, remember, is mu x. So d prime is becoming mu x plus p by mu, or x plus p by mu. And now finally I want to calculate this distance. Delta x. For that, if I take this distance as d double prime. Finally, my delta x, which is the shift, is d double prime minus d prime. Now d double prime is just x plus the thickness of the slab, and d prime from here we just saw it's x plus d prime. Very easily you prove this. So the point is not just a proof. You will see that how this can simplify things for us by a lot in certain type of questions. So I'll just minimize this a little bit into all the aspects. So this incidentally is also given as a proof example in H.C. Verma's solved examples. Somewhere around the 5th or 6th example, if I'm not mistaken. So this should become another everyday sort of tool or working formula that we use. Apparent depth, real depth formula, this formula. Then mirrors ke liye UV formula. Then next we'll be seeing lenses, lens makers formula. These are all the standard everyday tools that we use in solving every problem. But then again, there are always situations where we are dealing with non-paraxial rays, whether it be the case of refraction or even reflection. And the moment we are talking about non-paraxial rays, remember all these formulae don't work because they were for paraxial rays. So there you have to go back to the fundamentals. Snell's law if it is refraction, and laws of reflection if it is reflection. So the example we did of the the pole casting the shadow on inside water and all that, those are examples where you cannot apply real depth, apparent depth formula, or even the other question I was discussing. Okay, so hope this is clear. So now having done this, let us see how we will apply this directly. So for example, you can even apply this in real depth, apparent depth situation in a very clever manner. So let's see a typical type of problem where this simplifies life for us a lot. So consider we have this now. There's some kind of a vessel. Now this vessel has 2 layers of liquid. Let us say it has water up to here. And then it has some kind of oil up to here. Okay. So it has oil here. So this is water. So refractive index is 4/3. In fact, let's write this as mu W. Okay. And we also have above it an oil layer. Let's say the refractive index of oil is 1.2, so 6/5, something like this. Okay. And now what we have is we have got a point object over here and an observer who is viewing this more or less normally from above. And given to us that the oil layer is, let us say, 3.6 centimeters high, and the water is, let's say, 6 centimeters. Okay, so we have to find the depth of the object O, that point object, as seen by the observer, as seen from normally above. Yeah, so there are combination of methods that we can apply over here. So you can start by the ray diagram situation and first try to understand how many events are happening, and this is normal vision, so you can apply real depth, apparent depth version and try to find out the position. And then you can also think if we can somehow incorporate the slab formula that we just used and simplify the solution for us. So we'll actually do it by both the methods. Okay, 7.5 centimeters below. Okay, I'll just check your answer, Ganesh. Yes, your answer is correct, people. 7.5 is in fact the correct answer. From the surface of oil, it will appear at a depth below of 7.5. Very good. So in a question like this, immediately you see the advantage of using the slab formula. So if I were to start with the ray diagrams method, I would see that the rays coming from this, they first suffer a refraction like this, okay, and then again suffer a refraction like this. So if I were to produce these rays back, that would give me an image somewhere here. And then the second refraction, if I were to produce these rays back, they would give me, let's say, some here. And let us say this point is P. And also this point here is Q. So let's go with the real depth, apparent depth thing first. Okay. So if I were to look at the first refraction, the first event, it is from water to oil. So the apparent depth, which is now becoming QI1, because I1 is the image over here inside water, because you can see the refracted rays going in oil, they are produced back to meet the principal axis at I1. And this point here I have labeled this as Q. This one. So QI1 is the apparent depth, that should be equal to QO divided by refractive index of water with respect to oil. Okay. So QI1 should be the thickness of the water layer, which is 6 centimeters, divided by refractive index of water multiplied by refractive index of oil. So QI1 is becoming 6 multiplied by 6 by 5 divided by 4 by 3. So this is becoming how much? 6 into 6 into 3 divided by 4 into 5. Okay. So 36 into 3, so that is 108 divided by 20. So that is 5.4 centimeters. That is my QI1. So I'll just minimize this so that you can understand this fully. So this is the calculation for the first refraction. Okay, now let's come to the second event. Now for the second event, you can see that the refraction that we're talking about is happening from oil to air. So the real depth is the depth of the image I1, but with respect to which point? P, the surface of oil. So let's go back to the diagram, you'll understand. So for the second refraction, this point I1 is the object and refraction is happening at the top surface. So ये surface का point P से लेके I1, that is your real depth. So that is how much, that is the thickness of the oil layer, which was 3.6 centimeters plus QI1, which we just saw is that much, 5.4. 3.6 plus 5.4. So that is 9 centimeters. This is the real depth. And the apparent depth is PI2, and I2 is the final image. So that should be the real depth divided by refractive index of oil with respect to air. That is just the absolute refractive index of oil. So this will become 9 divided by 6 by 5. So that is how much? 7.5. Okay. So this is PI2, and I2 is the final image. But as you can see, this is tedious to solve. And if I have more number of layers where refraction is happening, it becomes much more tedious and becomes very, very difficult to solve. It becomes impractical to solve it within the time frame of the question. So that is why we are going to use a little trick here, that even though they are not exactly like separate slabs, but we can think of them virtually like slabs. Okay, people. So now let us see how we can use the slab formula very effectively over here. So aside from this problem, let's understand something before that. So if we have this situation that we have a combination of two slabs, one slab like this, let's say another slab like this. So they have some thickness T1 and T2 respectively, and they have refractive indices mu1 and mu2 respectively, and this gap between them is D, and we have a point object somewhere over here where this is X. And we have now, let's say, a couple of observers. One observer who's here, let's say E, and one observer who's here. So what will happen is that the position of the object as seen by observer E, it will have a shift of how much? T1 into 1 minus 1 by mu1 in this direction. So this guy will see the image somewhere here, let's say. This is the object as seen by E. Okay. Now you can see for the observer B, the rays coming out of here are further suffering refraction by the second one. So the rays which are incident on the second one, they actually appear to be coming from the first one's image. Okay. So now for B, the rays incident on the second slab appear to come from OE. Okay. So the net shift for B will be the shift for E plus some additional shift by the second slab. So it will be T1 into 1 minus 1 by mu plus the same thing for the second one, T2 into 1 minus 1 by mu. That will be the net shift. This is the combination of them. Okay. So what is happening is that you have these two slabs. Now any object seen through them, through the combination of them, it will appear to be over here. Let's say. But this is the net shift. Because this is what is happening in terms of rays. These rays bend, appear to come parallel to this somewhere here, and then again bend, and again come out parallel. And it is these final parallel rays, when you produce them back, they appear to come back. So the interesting thing, this delta X net, it is independent of both these things. It is independent of X, which is this distance, and the distance between the slabs. Okay. So if it's independent of this, that means that it's the same even for X tending to 0 and D tending to 0. And that is the situation we have in the above case. So it is not exactly like we have a separate water slab and an oil slab, because there is no air in between them. Okay. But again, it is that principle of refraction of light. It happens in such a way that if you have one medium here and another medium here, and you have some incident rays coming from this one, then they suppose go like this, and then again go like this. Okay. So you have this concept here that if let us say this angle is alpha. This angle here, let me just magnify this a little. So partly why this happens is because of this. If this angle is alpha, this angle here is beta, then this angle here is also beta because these are all parallel lines, and this angle is gamma. Okay. Now we can see that if this is refractive index mu1, this is refractive index mu, and this is refractive index mu2. So then you have mu1 sine alpha is equal to mu sine beta, which is then on the other side mu sine beta is equal to mu2 sine gamma. So if I remove the index in between, you still have mu1 sine alpha equal to mu2 sine gamma. So the in between medium of mu, if I remove that also, and I just created an interface between these two, I have mu1 on this side and I have mu2 on this side, and the incidence is happening in the same way at an angle alpha over here, then the refraction will happen in the same way. If this angle is alpha, then even though there is no in-between layer of mu, on mu2 it will come out with the same angle, gamma, which it was coming out above. Okay. So this concept, along with the concept that the lateral shift is independent of this distance d and the other distance x, these two will help you understand how we can reduce a problem like the previous one into a combination of two slabs. Okay, so I think this should be clear. Now let me apply all this to the previous question. And you'll see how that question becomes very, very simple to solve. So I had this thing. And we had a layer of oil and we had a layer of water. And we had a point object, which was over here. And we had an observer who was over here, vertically above. And we had this thickness 3.6, this thickness 6. And we had refractive index of oil 1.2 and refractive index of water 1.33 or whatever. Okay. Now let us compare this with a situation where this is what is happening, that we have an oil slab like this, and separately we have a water slab. So we have an oil slab whose thickness is 3.6 and same refractive index. And let's say we have kept them initially at some distance also, it doesn't matter. So we have the water slab of 6 centimeters. And we have actually kept a point object somewhere below. So we kept a point object here in this diagram, way below somewhere over here. And an observer is watching all this from above. So let's say we have this situation. This is the line of sight. So here for this point object, what will happen? The lateral shift or the shift along the principal axis will be such that this net shift will only depend on these two thicknesses. It will be independent of this distance and this distance. Be independent of these two. So delta x net will be equal to that thickness of the oil layer, which is 3.6 into 1 minus 1 upon refractive index of oil, plus the thickness of the water layer, 6 centimeters into 1 minus 1 by refractive index. So as you can see, this will become 3.6 divided by 6, plus this will become 6.0 divided by 4. So that is 0.6 here plus 1.5. So it's a 2.1 centimeter shift. Okay, delta x net is a 2.1 centimeter shift. Now what we do is, in the above diagram, for the case where d is tending to 0 and x is tending to 0, we have this only. We have oil, we have water, we have the point object here, and its image is here. And this shift is my delta x only. So now I want to find out this apparent depth, d prime. So as you can see, the apparent depth d prime will become the actual depth minus the shift. So the actual depth was this 3.6 plus 6. So 3.6 plus 6 minus the delta x, which we just saw above, was how much? It was something 2.1. Okay. So this is 9.6 minus 2.1. So it is 7.5 centimeters. So it is not just an approximation. You will understand that even if there is d is actually equal to 0, not tending to 0, so there is no air gap in between. But still, the angle of incidence and angle of reflection from water to oil will be the same as it would have been in that case, where there is an air gap in between. So that is why actually this gives you the exact case. We are not even doing any approximation here. It's giving you the exact case. The only approximation we have done is that we are understanding that it is only for the normal vision. Okay, so this is applicable only for an observer who's watching from directly above like this. If our observer is somewhere here or something, then he will see this point shifted somewhere here. You will not even see it on the same vertical line, because you can trace those rays and you can understand how they are going to be different. But in these cases, it is always going to be like this. So this is a very, very important shortcut trick formula for any combination of refractions at plane surfaces. Like that, we can have many layers of liquid. So there are a number of questions like that in HCV. So you can just reduce the different layers into imaginary slabs, even placing air gaps between them, and then apply the condition that that air gap's thickness is tending to 0. So the shift is still remaining the same. That was the whole point of this exercise over here, to understand this. So hope this is clear, people, and this will open up a lot of problems for you. You'll be able to solve a lot of questions very quickly, and sometimes even without making the proper ray diagram and all this like this. So by the time you become experts at this, you can do this question just by the direct formula now, which I've written over here. That the net shift is this much, and you'll understand. So the apparent depth from above will be that 3.6 minus the net shift. Okay, so this is all about refraction at plane surfaces. Okay. That question number 33 in HCV, I'll just give you a hint of how to do it since Ninad has asked it. But you will see that that is very similar to the problem where we looked at the shadow cast by the pole inside water. Okay, people, so hope this is clear. For just a moment, I will be unsharing the screen. I have to refresh my whiteboard software. When it gets overloaded with diagrams, it starts playing up. So just hang on a second. All right, almost there. Oh. So that question 33, I'll just give you a hint in HCV how to do it. Okay. So there you have a situation like this, that there is a point source of light which is underwater at a certain depth. And then there's a ceiling also above at a certain height which is known. Okay. And let's say over there actually there's a tire that is floating on water. Right? So I'll just, you'll understand what to do with the tire. So let's see, there's just a floating block over here. So the tire will become, this whole thing just rotated about an axis. So that is how the tire will look, because it has some thickness. Okay. Now you want to see what kind of shadow is cast by this box, this floating box, assuming it is opaque because of the source of light and the ceiling on top. So on the ceiling, what kind of image is formed of this, or what kind of shadow is cast. So just consider these rays now. Consider one ray which is just about missing this corner point here. So this ray, if it is just about missing this corner point, it will go somewhere here. Okay. So you would apply the laws of refraction, calculate based on the distances given this I and this R, and from that you would find the location of this point, let's say E prime. And similarly, now you consider another ray like this, which is incident just missing this corner here. So that one refracts and goes somewhere here. So this will have a different angle of incidence because it's a little different from here. So accordingly, it will have a different angle of refraction, and accordingly, this will finally intercept the ceiling at a point like this, B prime. So if this point is A on the surface of liquid and this point is B, okay, then that corresponds to a shadow A prime, B prime. So all the rays which are in between A and B, they are getting blocked. So they are not reaching the ceiling. So the ceiling is experiencing a shadow between A prime, B prime. Whereas all the rays which are before A over here, they are reaching the ceiling. Which are after B over here, they are reaching the ceiling. So that is how you will understand the position of the shadow. Now, of course, the position of this object has to be given in terms of this depth, okay, then this width over here and all that. So based on that, you will geometrically calculate these two angles, I and I prime. From that, you will get these two angles, R and R prime. And once you got R and R prime from Snell's law, you also know this height. So using trigonometry of this triangle, you know A prime's position. Using trigonometry of this triangle, you know B prime's position. So these are all basically geometry based problems. So the fundamental principle you are applying always is over here, Snell's law. Similarly, if it's a case of reflection, the fundamental principle you are using is this thing, laws of reflection. So for example, if we have an odd question in reflection like this, that you, let's say, have a concave mirror. Okay, this is the principal axis. So center of curvature is here and the pole is over here. Now suppose for some reason you are just asked to trace a ray diagram where you have a ray parallel to the principal axis, but it's not paraxial because it's not very close to the principal axis. So paraxial is nearly parallel and very close to the principal axis. Now suppose this is given to you that this is something significant like R by 3 or R by 4 or something like this. So then you have to trace where this thing is, where the reflected rays. So in this you will not be using that formula that 1 by F is equal to 2 by R, just because this is a ray parallel to the principal axis. It's parallel to the principal axis, but it is not going to go through the focal point. You will understand why it will not go through the focal point. Your focal point here is at the midpoint of the center of curvature and the pole, let's say somewhere over here. But for this particular ray, you can see that the angle of incidence is quite large. This theta is quite large, which you can calculate from trigonometry. So theta here is sine inverse of that thickness d, I mean this distance d, divided by r. So it's in fact sine inverse of 0.33. So that's definitely not a small angle. So after reflection, this will have a different kind of behavior. After reflection, this ray will actually go like this. And you can see in my diagram also, you can see it's pretty obvious that it shouldn't be passing through the focal point. So you'll actually have to calculate this by geometry now. So if this angle is theta also, right, then wherever the image is formed, you can again drop this perpendicular here and see this total angle is 2 theta now. Okay, so you can see that pi upon, so not even pi, you'll have to drop a perpendicular here and find this point q. Okay, so pi you want to find out. So for that, qi divided by this thing, this thickness. So that is how much d, which is whatever r by 2, is nothing but cot of this angle, and this total angle is how much? 2 theta. So this is going to be cot of 2 theta. So from that you will calculate qi, and once you calculated qi using the arc length over here and all that, you will calculate the extra distance qp. Okay, because this is 2 theta, na, this angle. So so using arc length and all, you can calculate this part, and from that you will finally calculate the value of vi. So it's purely a geometry based problem, along with the law of reflection, that angle of incidence is equal to angle of reflection. Here that alpha, beta, gamma derivation we are done to get the UV formula, that goes out of the box, because what's happening, your alpha, beta and gamma are not small angles here. Okay, so these are just some unusual questions which don't involve the standard formula, and for all other questions with normal vision or with paraxial rays, you have the standard formula that we're using. So that's something you have to be mindful of optics questions, particularly at JEE advanced level, because they always try to trick you with these things in JEE advanced. Whereas in mains, you need not bother too much. Most of the questions are going to be formula based. Okay? So now we come on to the final part of today's lecture, where we are moving on now to more cases of refraction. So we will see refraction at a spherical surface now. Okay, and we will see that just like for mirrors, spherical mirrors, we had 2 cases, convex and concave. Here we'll actually have 4 cases. Convex surface from denser to rarer, convex surface from rarer to denser, and vice versa for concave. But we'll see for all of them there is one common formula only. Okay, so let us get down to that. So suppose we have something like this. Let us say we have some kind of a medium. So it's having a spherical interface. This is my so-called principal axis, because I'm going to place my object on this axis, and the center of curvature is also on this axis. So this is a spherical refracting surface. And let us say this side has refractive index mu2 and this side has refractive index mu1. So in the example I've taken, let us say this is air and this is glass. So I will draw the ray diagram assuming that kind of thing is happening. Okay. Now deliberately I'll draw the diagram in such a way. Now see, center of curvature is somewhere here, let's say. Okay, and let us say I place some kind of an object, which could be like a small LED bulb inside the glass, or it could be just like a speck of dust or something like this. So this is my point object. So the line joining the center of curvature with the point object becomes my principal axis. Always that is the definition of principal axis. And pole of the mirror, or in this case pole of the refracting system, is just where that principal axis intersects the spherical surface. So that becomes my pole. Okay, so this is my principal axis. Now I have to find the image of that point object, or where that point object is observed to be for an observer who is over here, who's getting the normal view, who's getting the what we call the paraxial rays. Okay, so let us consider any arbitrary ray now, which in my diagram I'm going to draw as pretty divergent, but you will have to imagine that I'm talking about paraxial rays. Okay, so let me consider a ray which is incident somewhere over here. Let's see. Okay, so while I'm showing this incident ray like this, but we will later consider the case where alpha is a very small angle. So here I'll have to now apply Snell's law. Okay, so for Snell's law, let me first of all understand the normal at the point of incidence. So that is this line. All right, so this point of incidence is Q. Okay, so this angle here, this angle becomes the angle of incidence. This small angle here, it becomes the angle of incidence. Okay. Now remember, I have taken the case where it's glass to air, so it's going to bend away from the normal. Okay, so typically this ray after refraction, let's say, goes something like this. So this is the refracted ray, and therefore this angle here will become the angle of refraction. Okay, and more importantly, when I produce this ray back, it will be meeting the principal axis. So let me just clear out some space here. Oops. Okay. So the refracted ray I'm producing back now. So this refracted ray produced back is meeting the principal axis here. So this is the image that you're seeing. Okay. So again in my diagram, I will label some angles. So this angle I'm labeling as gamma. This angle I have already labeled earlier as alpha. And as usual, this angle here I'm labeling as beta. Okay, so it's again that whole game of alpha, beta, gamma, but only difference now is the relationship between I and R is not that they are equal. Okay, the relationship between I and R is now that mu1 sin I, or in this case mu2 sin I, is equal to mu1 sin R. Okay. And again, because alpha, beta, gamma are small angles, so I and R will also be small angles. So if we consider paraxial rays, we can do all this. Okay. So for paraxial rays, alpha is small, so automatically beta, gamma becomes small. And if you just understand geometrically in the diagram, this angle alpha is very small. Okay, oh, made a mistake here. This angle alpha is this one. So this angle here, this one is alpha. So if this is small, this point Q is very close to P. So all the angles involved become very small. So not only alpha is small, but all these angles also become small. Okay. But even before this, we have Snell's law, that is mu1 sine r is equal to mu2 sine I. Remember, here it is from glass to air. The refraction is from glass to air, so it is mu2 is the index of refraction on the incident side, mu1 is on the refracted side. Okay, so the moment we have these small angles, now we can say that mu1 r is approximately equal to mu2 I, because sine I is approximately I and sine r is approximately r. So now from here you realize how to proceed. Next, what we have to do is this formula of mu r with respect to I, we have to convert it to a formula between alpha, beta and gamma. And later we will convert alpha, beta and gamma into the object distance PO, the image distance PI, and the radius of curvature PC. And then of course we will use Cartesian sign convention. Okay. So I'd like you people to try and proceed from here yourself. I'll be putting up the equations in just a minute. Okay. But just see from here how we can proceed, and we want a relationship between alpha, beta and gamma. We want the relation between them. So for the relation we have Snell's law, which I've just told you. This formula Snell's law, this with the small angle approximation. Okay, so these are the fundamentals we are using. So convert Snell's law into that form where the angles are small, and then replace I and R in your figure with respect to alpha, beta and gamma. And then finally replace alpha, beta and gamma in terms of arc length and radius and all that. So replace it in terms of the object distance PO, the image distance PI, and the radius of curvature PC. So you will see, you will get that kind of relation. Okay, and then finally we'll incorporate Cartesian sign convention. So we'll get a UV kind of relation, relating UV with not only R, but also with mu1 and mu2. So that will become the required formula for solving this kind of refraction. Okay, people, so hope the diagram is clear, and just try to work out that relationship yourself. First, try to replace I and R in terms of alpha, beta and gamma. So you can use all these combination of triangles, OCQ, ICQ, or OIQ, any of these triangles involving the points I, O, and C with respect to the point of incidence Q. Okay, people, so let's take a look at what we can do here. Okay, so I'm just writing the formula beside over here. So first I will look at triangle. Sorry. Let me start with ICQ, is the easier one. Okay, so for triangle ICQ, you can see R is the exterior angle. or is also the interior opposite angle. So R is not the exterior angle. R is the angle IQC. That is nothing but R. Okay. And the angle ICQ is nothing but beta. Okay, so these are the interior angles. And the exterior angle is this one, QIP, which is gamma. This is the exterior opposite angle. So we have gamma is equal to R plus beta. Okay. So hope this equation is clear to all of you. So I'll just magnify this and help you understand what I'm doing. So I'm considering this larger triangle. So just follow my cursor. So I'm considering this larger triangle ICQ, this triangle here. Okay. So now in this triangle ICQ, you can see that this angle over here, this is the angle between the normal and the refracted ray produced back. So that is nothing but this angle R. And this angle I have already labeled as beta. And this angle is the exterior angle. So gamma is equal to this angle, which is R, plus this angle, which is beta. So that's how I get the relation that gamma is equal to R plus beta. So I'll just write it for future reference over here. So gamma is equal to R plus beta, or I can replace R with gamma minus beta. That's my first equation. Okay. So now going back to the diagram, I have to fish out another equation from there involving I, and then we are good to go. Okay. So I will just make some space over here. So I want something involving I. Okay. So I, you can see, is which angle over here? Yeah, OCQ is the angle. So I is the angle which is made with the incident ray with respect to the normal. So it is angle OQC. Okay, so I want that triangle OCQ. It becomes very obvious that I need to apply that triangle. So triangle OCQ, you can see that angle OQC by definition is the angle of incidence, because OQ is the incident ray and CQ is the normal. Okay, and then of course I have angle OCQ is defined as beta, and I have angle QOP which I have defined as alpha. Okay, so this is the exterior angle and this is the interior opposite angles. So we have alpha is equal to I plus beta. That's our second equation. Okay. So I'll just magnify this a little and again explain this to you. So now I am considering this triangle. Just follow my cursor. So OCQ, this triangle. Okay. So I'm considering this triangle, OCQ. Now in this triangle, you can see that this angle, the angle of OQ, which is the incident ray with respect to the normal CQ, is nothing but the angle of incidence, I. Okay. And this angle, the exterior angle, that is the angle that this incident ray is making with the principal axis. So that is defined as alpha. Okay. And of course, this angle is beta. So exterior angle alpha is equal to sum of interior opposite, that is beta plus I. So exterior angle alpha was equal to I plus beta, or angle of incidence is now equal to alpha minus beta. That becomes my second. Okay. Or you can say this is my second and this is my third, because this was your important first equation. So now we just substitute. So mu1 into I, mu2 into I, just remember it is from is equal to mu1 into gamma minus beta. So I have, let's keep the beta terms on one side. So mu1 minus mu2 into beta is equal to mu1 gamma minus mu2 alpha. Okay. Or properly now I can write this as refractive index of air minus refractive index of glass into beta. Now beta I can approximate as arc length PQ divided by PC. Okay. And that is equal to refractive index of air into, so approximately equal to arc length PQ upon Pi. We refer to the diagram, you will understand, minus refractive index of glass into arc length PQ divided by this thing, PU. So now I have this formula that refractive index of air divided by the image distance minus refractive index of glass divided by the object distance is equal to difference of the refractive indices of air minus glass divided by the radius of curvature. So this is the formula that we are getting in terms of Pi, PO and PC. And now we will incorporate Cartesian sign convention into this. So deliberately I have taken a diagram which is like, normally we take the object on the left hand side and the image on that side and all that. But here I have taken the object is on the positive side. But you will see that when we incorporate Cartesian sign convention, it's all the same. So I'll just take you back to the diagram so that you understand the definition of alpha, beta and gamma. So in the diagram here, you can see that alpha is approximately equal to arc length PQ divided by PU. Beta is exactly equal to arc length PQ divided by PC. And gamma is again approximately equal to arc length PQ divided by Pi. Okay, so finally, now let us incorporate the sign convention in this and understand this in totality. So if I'm going with the sign convention, Cartesian, I'll take this side as positive and this side as negative. So my image was also here, my center of curvature was also here, my object was also here. I mean, object might have been on here, it doesn't matter. So you can see that in this case, U is also positive of PU, V is also positive of PI, and R is also positive of PC. So substituting the formula, what we are getting is for refraction from glass to air, we are getting refractive index of air divided by V minus refractive index of glass divided by U is equal to refractive index of air minus refractive index of glass divided by R. So now, like this formula over here, we can build actually 4 cases. Here we have seen refraction is actually happening through a concave surface, because if you see the incident rays, they are incident on what kind of a refracting surface? A concave surface. Okay, and it is separating a denser to rarer. So this is the case that we have got. So this formula that we got earlier over here, this is for a concave surface and denser to rarer. That is the case. Now you'll see that for each of the 4 cases, your distance formula will be different. PO, PI, that formula will be different, but this will be same. So this is a universal formula for all cases. Actually, not exactly this. You can say that if you can convert the universal formula like this, that refraction from medium A to medium B, this case. So mu B upon V minus mu A upon U is equal to mu B minus mu A upon R. This is, you can say, the general formula which will be applicable in all cases. Okay. So this is universal. Okay. That is, mu A is greater than mu B. Okay. Convex and concave surface, or mu A is less than mu B. Both concave and convex surface. So we have taken only one of these cases. We have taken the case where A to B. So mu A is greater than mu B, and it was a concave surface. But if you repeat the derivation, you will see with the Cartesian sign convention. Okay, with Cartesian sign, the formula is universal. Whereas without the sign put in, of course, it can vary from case to case. Okay, so this is the situation. Okay, and also you can see that for a plane surface, R is tending to infinity. So we have mu B by V minus mu A by U is equal to 0. So we have V is equal to U into mu B by mu A, or we have apparent depth is equal to real depth upon refractive index of A with respect to B. And this was a refraction from A to B. Remember. So that we are back to that formula. So even that formula becomes a special case where the sphericality of the refracting surface is that it's an infinite radius. So the refracting surface is a spherical surface which is tending to become plane. Okay, so I would advise you to just take some examples yourself for working out the other 3 cases which we have not discussed. You can take numerical examples, you can take just the ray diagram kind of general ray diagram kind of situation, and you will see that you will get all sorts of combinations for you will get virtual image, you'll get real image, everything like that. But you will see that with the sign convention, the formula always reduces to this, that if the refraction is happening from medium A to medium B, it is mu B upon V minus mu A upon U is equal to mu B minus mu A upon R, where remember everything including R is with the Cartesian sign. Okay, so hope this bit is clear to all of you. So let's wind this up with a quick application question. Imagine now we have something like this. We have a solid glass sphere. It has radius equal to whatever, let's say 24 centimeters, and refractive index of glass is 3/2. Okay. Now, this is the center of curvature. Okay. Now there is again some kind of a bubble or something in the glass, or a dust particle, which is like a point object, which is over here, where the distance OC is, let us say, equal to 8 centimeters. So on one side of the, there's just a dust particle or some particle inside glass, which is at a distance of 8 centimeters from the center of curvature. Now, there are two observers. One guy here who's observing it normally from this side, and there's another observer here who's observing it normally from the other side. So you have to find the position of the object as seen by A. So for A, the glass surface is here. So this is the pole as far as A is concerned. So with respect to this glass surface, at what depth he is seeing that object. And similarly for the observer B, this point is the surface PB. So with respect to PB, where he is seeing. Okay, so find the position of point object O, which you can think of just like a small particle, as seen by observer A and observer B. Okay, with respect to their respective poles. Okay, so just try this out, and you don't need to switch sign convention. You can just keep the same sign convention for both the calculations you're doing. When you are calculating for A, keep the left side of P, or PA rather, as your negative side and the right side as your positive side. And then again, when you're doing the calculation for the second one, B, you apply the same thing. Left of PB you take as negative, and right of PB you take as positive. You don't need to switch. That is the advantage of the Cartesian sign convention. So just try out the answers of this. The radius is, yeah, and just scroll up. It was 24 centimeters, I think. Yeah. So the radius is 24 centimeters. The distance OC is 8. Now we just find the position of the image as seen by A and B. Okay, so I've started getting some answers. For A, yes, Ganesh, that's correct. So let me solve each case individually. So for A, the situation is something like this. This is my second medium. So glassy. Okay. Now the center of curvature is here, the object is here, the pole is here, and the observer is on this side. So taking this side as positive, and this side as negative, I will take U as positive of OP, which will be how much? It will be 16 centimeters, correct? Because OC was 8 and it was 24, and R will be positive of PC, so that is plus 24, okay. And it is glass to air, so that means I have to take mu A as 3 by 2 and mu B as 1. So mu B upon V minus mu A upon U is equal to mu B minus mu A by R. So 1 by V minus 3 by 2 divided by plus 16 should be equal to 1 minus 3 by 2 divided by plus 24. So let's solve this. So we should be getting 1 by V minus 3 by 32 is equal to minus 1 by 48. So 1 by V is becoming 3 by 32 minus 1 by 48. So here we can take 8 common. So we could have taken 16 common actually. This makes life easier. So 16 2s are and 16 3s are. Okay. So 3 by 2 minus 1 by 3 will give us how much now? 6 minus 2, so that is 4 by 6. No, sorry, 9 minus 2, so 7 by 6. Is that correct? Okay. But more importantly, you can see we are getting V as a positive quantity. So V is positive of 96 divided by 7. So that is positive of approximately 13.9. Sorry, 13.7. So let us understand in terms of diagram what that means. So in terms of the diagram, what that means is, let's see, any ray of light from E will tend to bend away from the normal. So this is the normal. So as it bends away from the normal, it will go like this. So when you produce this back, I'll give you an image somewhere over here. So that is why the distance PO was 16 centimeters and the distance PI is coming less than that, is coming about this much centimeter. You can check my final calculation, it might be slightly different also, but seems correct. Alright, so for E, O appears 13.7 centimeters behind the pole. Okay, so it is a virtual image, as you can see. Now similarly, let's move on to the case of B. So for the case of B, the refracting surface is now this side. The center of curvature is here, but the object is here. The pole is here. So this time let's demonstrate what's happening in the ray diagram first. Then we'll do the calculation. So the incident ray over here, let's say. Now imagine this biraxial is actually very close. Okay. So this is the normal. Now it will bend away from the normal. So this is going to a rarer medium. So it will tend to go like this. So when we produce this back, tend to give an image which is further behind. So this is what we should expect. We should expect a virtual image which is at a distance of more than PO. Okay. So anyway, so this time we're taking this side as positive, this side as negative. So we'll take the radius of curvature as minus, the position of the center of curvature is minus PC. So that is minus 24 centimeters. We'll take U as minus PO, which will become minus 32 centimeters. Okay. And V we want to find out, and it is refraction from glass to air. So again, our mu A is 3 by 2 and our mu B is 1. So let us apply the formula. So mu 2 by V minus mu 1, which is 3 by 2 divided by U, is equal to mu 2 minus mu 1 divided by R. Okay, so this time you see we get 1 by V is equal to 1 upon 16, this one, minus half upon, 1 upon 48. But with a positive sign, 1 upon 48, and this will come with a negative sign, 3 by 64. Okay. So 4 minus 9 by 12 into 1 by 16. That's my 1 by V. So V comes out to be 12 into 16 by minus 5. So that is 192 by minus 5. So V comes out to be minus of 0 So this still means it's a virtual image only because it's on the same side. Okay, so virtual image seen by B 38.4 centimeters behind the pole. So this becomes this. So this is how we apply with various situations, concave, convex. In this case, both the versions we saw is from denser to rarer, and both were from concave surfaces. But one was where the object is behind the center of curvature, one was where the object is in front of center of curvature. So we got virtual images in both cases, but one where it came further in front, one where it went further behind. So, various such type of combinations of questions and applications you will see. But most importantly, what we will see next time is the application of this concept to two refractions back to back happening from surfaces, spherical surfaces, which are very close to each other, which is nothing but a thin lens. Okay, a thin lens is nothing but an optical medium like glass or something, which is bounded by two very close spherical surfaces. So either surface of the lens is a spherical surface, but their poles are almost at the same position. The thickness of the lens is very small compared to the radii of curvature. That is what we mean by a thin lens. And how we derive the focal length of a thin lens is by applying the concept of the refraction at spherical surface, but in series, one after the other. And from that we get what is called the lens maker's formula. So that's why we'll continue next time. So you can continue with H.C. Verma and booklet problems, especially ones involving combination of mirrors with refraction, refraction at plane surface, refraction due to slab, refraction at spherical surface, all these kind of things. For example, there are questions like this where you have a glass sphere like this one, but it is silvered from this side, and there's an object somewhere over here, and you have to find the image. So you can see that for this object there is refraction from air to glass at spherical surface, then reflection by a plane mirror, by a spherical mirror, then again refraction from glass to air. So three things you'll have to apply in series, and those kind of things. So there are some interesting questions in HCV as well as your booklet. Actually, geometrical optics HCV has a very good collection of questions. Apart from relative motion, it has all types of questions. So we will be discussing more things about relative motion also as we go along, like we did for spherical mirrors last time. Okay. So that's it for today's lecture, people. Hope you are all doing fine and in good spirits in spite of the extended lockdown and things like that. I know it is very frustrating for everyone, and I am foremost among the frustrated people. But at the same time, we have to make this time productive. Okay, so let's at least keep our studies in order with online lectures and a lot of problem solving at home. And the rest of the time, you try to enjoy with your family, help out your parents with all the work at home, and spend some good quality time with them, playing some board games or watching some old movies together or reading books or whatever family activity. But parents, siblings, everybody at home, try to keep them in good spirits with your own enthusiasm. Okay. So that's it for me today, guys, and all the best, and hope all of you understood this lecture. Let me know. I'll be sending you the recording and the whiteboard notes very, very soon. So God bless.